Hello, my name is Troy, and today we are going to be working on section 4.4, which is factoring polynomials, and this is from Algebra 2. So when we say we are factoring something, we should at this point know how to factor quadratics equations. And as a reminder, a quadratic equation is a type of polynomial that is a second degree polynomial and is written in standard form, ax squared plus bx plus c. And we've learned a couple different techniques to factor quadratics, and today we're going to move on to learning techniques about how to factor polynomials in general. So polynomials can have any number of terms and they can have as high of a degree as they want. So that means now we have to develop new techniques to factor these polynomials. And we'll talk about four of those techniques today. However, we can't forget how to factor quadratics as well, because that will most definitely show up in certain steps of factoring polynomials. Okay, so let's get started with the first technique. And this is really a technique we should always be looking for when we're factoring anything, which is looking for a greatest common factor. So when we look for greatest common factor, we have to make sure each term has that common factor, um, has a factor in common, right? And then we can just factor it out and write what's remaining in the parentheses. So let's practice some GCF here. So factor the polynomial completely. We can see here in number 5, we do not have a quadratic equation, but rather a third degree expression, right? But if we look at each term in this expression, we can see that they each have a factor of x, right? They're each being multiplied by at least one x. So we can factor out x, and we can write this as x times x squared minus 2x. Notice I'm just taking away one factor of x for each of these terms. And this one only had one x, so now this is minus 24. Okay, so we factored this polynomial, but we have not factored it completely yet, right? But we now notice that we are left with this, which is a quadratic. And so now is when we get to use our quadratic factoring techniques. I usually would use the x method here and write negative 24 and negative 2 here. And I'm looking for two numbers that multiply to become negative 24, so a positive and a negative. And they add to be negative 2. So let's see, 8 and 3, that wouldn't work. 6 and 4, that would work because they have a difference of 2. And that means I have to have the 6 as negative. So 6 and 4. Okay, and now we can't forget about that x that's still written out there, but now I'm factoring that green expression, the expression underlined in green. I'm factoring it out this way, right? So now it's x minus 6 times x plus 4. And that is now factored completely because these factors are prime, right? They cannot be factored anymore. X minus 6, and x plus 4, those are as factored as possible. And so there's our solution. Okay, so we factored that completely. Now let's practice another one, number 6 here. So we notice number 6 only has two terms, but they both have a k. In fact, they both have at least 3 copies of k. And also their coefficients have a greatest common factor as well. So we can say that the entire GCF here, well, 100 is divisible by 4, and obviously 4 is. So 4, and then they each have at least 3 k's, so 4k to the power of 3. Okay, and what does that leave us with in here? Well, we took away this entire 4, so there's going to be no more coefficient on this left term, but there are still 2 k's remaining, so k squared minus, and then 100 divided by 4, that would be 25. But we took away all of the k's, all 3 k's being multiplied, and so therefore it's just 25 here. Once again, we're not finished because we need to continue to factor. So in this case, you should have learned by this point something called a difference of squares. And so K squared and 25 are both perfect squares, so we can apply our difference of squares here to get K plus 5 and K minus 5. And then I cannot forget to drop down this factor as well. So that was just 4K to the third. And now this is factored completely. Notice I don't need to put the 4K to the third in parentheses because there's no plus or minus in there, but you can if you want. But this is now factored completely, so our problem is finished. So a lot of these problems are going to be kind of using our technique to turn it into something that is then a quadratic and then factoring it from there. Okay, let's quickly go through this last one and then move on to the next technique. So I noticed that they each are divisible by 2 for sure. So 2. And then how many m's do they have? Well, it's as simple as just looking at the lowest degree, right? It's 4 m's at the minimum. So 2m to the 4th. Okay, and now I'm left with m squared minus 12m plus 32. Okay, and now I can factor that out using the x method. So I would be looking for two numbers that multiply to positive 32 and add to be negative 12. Well, I know that 8 and 4 multiply to be 32, but they add to be positive 12, so I can use negative 8 and negative 4. So x minus 8, x minus 4. And obviously you could use the x method on that just to kind of keep everything written down. But you don't always have to use the x method. Okay, and then I once again need to write down this. And so probably a good idea to write that down first just so we don't forget as well. But there's our fully factored form of this expression here. Okay, so that's technique 1. And one thing about GCF is that we should always be trying to find a GCF like right off the bat. And then from there, we might need to use other techniques, but the GCF should always be the first thing that we're looking for. So that's kind of the first order of business. Okay, next we're going to talk about something called a sum or difference of cubes. So we quickly covered a difference of squares up here, right? So k squared minus 25, that we would call a difference of squares because it's two perfect squares that are being subtracted, meaning a difference. However, we also have a special pattern that we can detect when there is a difference of cubes or even a sum of cubes, meaning perfect cubes. So things like x cubed, a cubed, also numbers, right? 2 cubed would be 8. 3 cubed is 27. 3 times 3 times 3. 4 cubed is 64. These are all perfect cubes. In fact, any variable with an exponent that has 3 as a factor should be a perfect cube technically. But we're really focusing on these ones to start off at least. Okay. Cool. And obviously any letter, any variable cubed is a perfect cube, not just x and a. Okay, so here is the pattern here. I just grabbed a picture. So the acronym to memorize here is SOAP. So kind of similar to like foil. Well, it's not similar, but it's like a 4-letter word that we use to like remember this acronym, SOAP. Okay, so S stands for same, O stands for opposite, and AP stands for always positive. Well, what does that mean? Well, that is kind of telling us how to set up our result based on whether it was a sum of cubes or a difference of cubes. So same means it should be the same sign. So look at here, we have a minus sign. So this was a difference of cubes. So the first thing we write is a minus, and this A and this B are always just going to be there, right? So whatever the cubed root of that factor or of that term was, and then whatever the cubed root of this term were, go right here. But notice down here, it was a plus. So instead of A minus B, it's A plus B. So we have to kind of change our pattern based on whether we had a sum of cubes or difference of cubes. Now for opposite, it means change that sign. So the minus creates a plus and the plus creates a minus. These need to be opposites. And then purple is saying always positive, right? So no matter what, this third one is going to be a plus. But notice the difference in the pattern between difference of cubes versus sum of cubes. Okay, so let's practice this and just kind of practice putting it into this form here. So right here, number 13, we have a sum of cubes, right? It's a cube plus a cube. We talked about how this is 4 cubed. So we can write this down as, remember, we're kind of looking for a squared, and it's a sum, so a squared plus b squared. So if we want, we can write this down as x, or sorry, not squared, I should be saying cubed. Cubed and cubed, x cubed plus 4 cubed. And now we can fill it in to this perfect square SOAP pattern. Okay, so this equals, and I should be using this bottom one for the sum. So it's a plus b. Well, a is just x, and b is just 4, so plus 4. This plus is coming from the always, or not always positive, but rather same. That's SOAP same. And then there's another factor here, which is a squared minus ab. Okay, so a squared would be x squared squared. Now minus, because that is the opposite sign, so it was plus, so this is a minus. And then a times b, so that's x times 4, or 4x. And then always positive, so I'm always writing plus here. And then b squared, so that's 4 squared, or I can write 16, right? Okay, so we had same, opposite, and always positive. And this is the technique you always want to use to factor a sum of cubes, and then we'll do a difference of cubes next. But notice how just like in a lot of other problems, we're not quite done yet because we want to now check if we can factor this. Okay, and we can see 8 and 2 are factors of 16, but those aren't going to get us to -4. And then 4 and 4 is definitely not going to get us to -4. So unfortunately, there's nothing more we can do to factor this. So we just say that we are now complete. That is fully factored. Boom. Okay, and oftentimes with SOAP, that's how it's going to be, but you do want to check if that can be factored. So let's do it with c cubed minus 27 now. Okay, so that's the same as c cubed minus 3 cubed. And that is going to equal, well, now we need to use this top pattern where it's using a minus, right? So, but instead of looking up there, we'll just use our acronym SOAP. So let's do, we know this gets filled in with A and B, aka C and 3, so C and 3. Now, what sign do we use? Well, we're using SOAP, so we should use this sign. And I guess that's not consistent colored, so I'll use green here, yeah. So it should be a minus, because same, okay? Now in here, there's 3 terms. There's a squared, so that's c squared. There's ab, so 3c. And then there's b squared. And remember, I'm talking about these a's and b's, which are just in the general form for this. So that would be 3 squared or 9. Okay, and now what do I put for the signs? Well, it's same, we already did that. Opposite, so now we need the opposite sign here, and then always positive goes here. So opposite of minus is going to be a plus, so a plus there, and then always positive is always a plus, so a plus there as well. Now we can check if this is factorable. 9 and 3, it's not, because the only factors of 9 are 3 and 3, so that's not going to work. So we're done there. Okay. Oh, I forgot to start my timer again. All right. Cool. I think, and then I'll just leave this one. So, or actually, let's first talk about how to kind of set this one up, but then I'm going to move on. So because this one isn't like, this doesn't like look like a perfect cube, especially because of that 7 right there and this 4 right here. We need to use something else, but remember we talked about how we always want to start off by checking if you can factor out the GCF. And in this case, we definitely can. So 16 and 250, 250 is not divisible by 16. It's not divisible by 8, and it's not divisible by 4. Um, and I know that because 50 is not divisible by 4. So all I can factor out here is 2. So 2, but then I can factor out a lot of t's, right? 4 of them to be exact. So it's 2t to the 4th times, okay, now I have 8t cubed plus 125. And if you examine the inside of these parentheses here, this is most definitely a sum of cubes because 8t to the 3rd, we can write that as 2t cubed because 2 cubed is 8 and t cubed is t to the 3rd. And then 125 we can write as 5 cubed. And then from there, we're plugging all this stuff into SOAP. Cool. But let's move on to the next technique here, which is called factoring by grouping. So you might have done this before with quadratics, actually, especially when you have like when you're using the x method and instead of, so remember we have ax squared plus bx plus c. A lot of times when the a is greater than 1, so like it's there at all basically, you end up using factoring by grouping. There's different ways to do it, so this might be new to you or this might look familiar. But factoring by grouping actually just works in general. You don't need to have come from the X method to be using it. Factoring by grouping is simply grouping your polynomial into 2 different groups, always just 2, at least for these purposes. And it's almost always going to be the group of the 2 on the left and then the group of the 2 on the right. Sometimes you might need to rearrange it, but that's usually you can just kind of group them like this. And then sometimes what you'll see is that you then draw a horizontal or a vertical line right down the middle like this. And now we're going to sort of solve each group separately. And what do I mean by solve it? Well, we're not technically solving anything, but we are going to simplify it by using a GCF. So we're now looking for a GCF in this yellow group. So there's no coefficient for this y, so there's no coefficient, but we do have y squared as our GCF. Okay, and then that leaves us with y minus 5. Okay, awesome. And now I'm going to come over to this right side and factor this one with a GCF. Well, there's no y I can take out, but there is coefficients, right? 30 is divisible by 6, so I can take out that 6 and say this leaves us with y minus 5. Okay, awesome. And so what we now see is that we are left with the inside of the parentheses being y minus 5 in both cases. And this is always the idea with factoring by grouping, because in order to use factoring by grouping, this needs to be the case. So if that's not the case, either check again or maybe factoring by grouping isn't the correct method to use. But if it is, then it should always work out like this. Okay, so where do we go from here? Well, our answer is always going to be in the format of 2 factors. And it's always 2 binomials, unless you had more than 4 to start with. But one of those factors is simply just going to be what we have in purple right now. It can either be the first one or the second one, but you never write it down twice. So the whole idea is that it shows up twice. It shows up in each of these, but in our final solution, we only write it down right there. The other factor that we write down is actually coming from what we factored out, as you might be able to guess. So basically this 6 and this y squared get placed together. It's almost like you're combining like terms with the pink parentheses term or factor being the like variable that's allowing you to combine. So y squared and 6 combine to be y squared plus 6. Okay, and it's plus because notice I didn't factor out a -6 or anything, so I can write the +6 to indicate I factored out a +6 if I want. But yeah, sometimes you will notice that you need to factor out something negative in order to properly factor by grouping. So let's check out this one. It involves some negatives. So, and once again, you can't factor y squared plus 6 anymore, so that is fully factored up top. Okay, so let's factor this by grouping. Notice I'm drawing this line with the negative sign, which belongs to that 4x, right? It's a -4x, so I'm keeping that over there. Okay, so what can I factor out of here? Well, x squared, and then I'm left with x minus 8. Okay, awesome. So I already know I'm looking to get x minus 8 here, and that might change what I want to factor out, right? So I could factor out a 4, or I could factor out a -4. Well, I know I want this to turn negative, and I would need the x to be positive, so that makes me know that I want to factor out a -4. So I'm factoring out -4, so that what I'm left with is x minus 8. And so that's kind of the flexibility that you have, is you can factor out negative or positive, and that should change what shows up here, which is important because we need these to be the same, right? So x minus 8, x minus 8. Okay, now we are left with x squared minus 4, right? So I combine the two things we factored out, and it's a minus since that was a -4. And then the x minus 8, which appeared twice. Okay, then this factors to, it looks like x plus 2 and x minus 2. And then that's still there. Okay, I'll let that one be an exercise to do on your own if you want. So 16n to the third plus 32n squared minus n minus 2. Not too different than the ones we've already done, except I think in this case, what's going to happen is, notice there is no GCF. So if we had to find a GCF here, it's either just 1 or -1. In this case, it would be -1, so that this leaves you with n plus 2, right? Because you can tell that's what's going to come out of this one as well. So let's move on to the fourth technique here. And the fourth technique it is a technique, but it's not like necessarily anything too new. It might be something that you've seen before. And that's simply by thinking about polynomials as if they are quadratics, even if they're not. And that's not always possible, but a lot of times it is. So for example, in number 31 here, we couldn't necessarily call this a quadratic equation, but it does most definitely look like something we can factor with a difference of squares, because this is a square and this is a square. So we can, if we want, we can turn this into a quadratic by saying, all right, well, what is this actually equal to? Well, that's 7k squared and then minus 9 here. And why did I do that? Well, technically that turns it into ax squared plus bx, but there just is no b, and then plus c, right? And so by doing that, I've turned it into a quadratic, and I can solve this as if it was an a squared minus b squared problem. Okay, and that would give us a plus b times a minus b. And so therefore we have 7k plus, and then 9 is 3 squared, so plus 3, 7k minus 3. So that might look new to you. That might be something you've already known how to do, but it's sort of just thinking about polynomials as if they were quadratics and then using our familiar quadratic techniques. But here's another case where like you totally could do that, but you definitely don't have to. So let's talk about both ways to solve this. So first, let's solve it by treating this as a quadratic. So how can we write this as ax squared plus bx plus c. Well, clearly I want this to just be c, so it looks like my x should sort of be, um, or I guess the better way to think about this is if this one should be ax squared, I need to figure out like what this would be squared. But there is no square root of 3, so either way, like the first thing you have to do here is factor out at least that 3. So it would give us 3 times r to the 8th plus r to the 5th minus 20 r squared. Okay. But then, or sorry, and I totally forgot to factor out the r as well here. So first I thought you didn't have to do it, but you definitely do have to do that. So I'll just do it in this next step here. So which equals 3r, because I can factor out at least 2 r's, 3r squared times r to the 6th now, plus r to the 3rd minus 20. Okay, and now we can see what this problem is kind of getting at, which is that this in pink now is not technically a quadratic expression, but we can definitely turn it into one by saying that this is just something squared plus something minus 20, and we know that that something is r to the 3rd. And what is being squared? Well, it's technically r to the 3rd squared. And so our x that we usually use to factor is technically r to the 3rd in this case, and there really is no coefficient at all. So it's sort of now using the x method to say what two numbers can add up to just 1, because the coefficient here is 1, and then multiply to be negative 20. That's going to be 5 and 4, specifically negative 5 and positive 4. No, sorry, negative 4 and positive 5. I don't know why I said it backwards. Okay, and so now our solution is r to the 3rd, right? Because it's not just r, but r to the 3rd is sort of what we're using as our x. R to the 3rd minus 4 times r to the 3rd minus 5, or plus 5, sorry. And remember, we still had that 3r squared in there as well. And so there is our solution. Okay, why don't we end it right there? There's a couple more parts of the book, but they have more to do with like applying this stuff. So check it out if you want. Do some practice problems. But yeah, these are sort of the 4 new techniques that we're learning here to factor polynomials.